Hey guys, it's Professor Goodman. We're going to go over our homework that's going to be coming up next week. So this is all of chapter 16. So for your Longitude work and your eMath, it's going to be all of chapter 16. So we have 16.1 and 16.2. This is not going to be as much problems or as many problems as there were last week, but these problems are going to start getting a little more difficult. So these guys, we're doing distribution of differences in sample proportions. This means if we're looking at differences, we have to have at least two different samples for our proportions to have a difference. So if you guessed that we're going to be doing formulas with two different samples and two different p-hats, you are correct. So it's definitely a new bird. So thankfully, there's only I think 15 total questions. Like there's 5 in 16.1, and then there's 10 in 16.2. So we'll go through some of those, and hopefully it helps out. Okay, so first things first, let's look to see what kind of problems we might expect to see in a distribution of differences in sample proportions. A pharmaceutical company tests its new product to reduce joint pain on 1,000 people. Okay, so of those 1,000 people, 700 were given the drug. Okay, so we're splitting these 1,000 people up into two groups, it looks like. 700 people were given the drug, and 585 of those report that they do not feel back pain after the drug. Okay, so then my proportion for this would be, out of those 700 people given the drug, this many felt that they do not have joint pain after taking the drug. So that's for my caveman definition of probability, it's what I wanted, right? The 585 divided by 700. That'll be my p-hat 1. Okay, so let's keep reading on. So then they said the 300 people, so 300 people out of those 700 that were left were given the placebo, which means, the control group. They were given something that looked identical to the drug that the other people were given, and they were asked, how do you feel about this? Not knowing that their drug that they were given was a fake. And then 144 people said that they did not feel joint pain after taking it. So I guess, yeah, that placebo, man, that they were like, oh, this definitely does help. But anyway, let the experimental group be the people who took the drug. The proportion of those who reported the drug was effective is denoted p hat sub e. And then let the control group be people who took the placebo. Proportion of those who reported the placebo was effective is denoted p hat sub c. So now we want to find the difference between p hat sub e and p hat sub c. Now, sub E and sub C, that's really focusing in on this problem. So I'm just going to say p hat 1, p hat 2. And we'll just say maybe p hat 1 is my p hat E. So it's not fat A or fat T, I don't know. But then we have p hat C. Okay, so these are my different p hats. I usually just do p hat 1, p hat 2 because it's easier for me to type, and it works for all the problems. Okay, so let's check this out. So first off, let's find our p-hats. So it says 700 people were given the drug, and 585 of those did not feel joint pain. Okay, so that means out of our 700 people, 585 did not feel the joint pain. So our p-hat would be 585 divided by 700. Okay, so make sure you put an equals before that to open yourself up to the math world. Okay, and then my p-hat 2. Sorry about that. Ugh. I always have an even number of sneezes. I don't know why. Anyway, so now we're looking at the other p-hat, right? So our p-hat 2. So 300 people were given the placebo, and 144 report they do not feel a joint pain. So it'll be my 144 divided by 300. Okay, so these are my two p-hats, right? So now they want to know what's the difference of my two different p-hats. So they want, it's usually always your p hat 1 minus p hat 2, or in this case, the first one they chose is just p hat e. So you just do p hat 1 minus p hat 2. So go ahead and do that in this cell. So I click on my p hat 1, subtract off my p hat 2, and voila, that's the difference in proportions. So there's about a 35% difference between the people who took the drug and felt that it was like they didn't feel joint pain, and then p hat 2, same thing. So the increase is about 35%. So it's pretty good. So we're gonna look at this stuff. So first off, that's it for this problem. Now it says assume the treatment is a 40% increase in joint pain. So it's about 35% is the true value, but let's see. So assume the treatment effect is a 40% increase in joint pain relief with a standard error of 7%. So think of the standard error as almost being kind of like your standard deviation. It's just that we can't really call it a standard deviation just because it's using two different samples, but it's pretty much a standard deviation. So that's why I put here, when you see standard error, think of it like a standard deviation, but for 2 samples instead of just 1. Okay, because the formula is pretty much the same. You're just going to it's going to be the same 2 parts of a formula. The only difference is you're summing the 2 different parts together. You'll see that in a second. All right. So what analysis and conclusions can be drawn? All right. Well, think about this. If there's a 40% increase in pain relief, how many standard deviations is that away from our p hat 1 minus p hat 2? Well, a standard error is 7%. So that means if I subtract 7% from my 40%, I get to 33%, right? So if I do my 0.4 minus 0.7, 0.07, sorry, I get to 33%. So that means this 35% is within 1 standard deviation of the difference, I guess. So that's a problem, right? It's within 1 standard deviation. Remember from our hypothesis testing, what do you guys think we're going to do? That means it's probably going to fail. It's going to fall into the fail to reject the null hypothesis region, right? Being 1 standard deviation away is not too big. So right away it would say the results are not statistically significant because our calculated value of 35.57 is within 1 standard error of the mean, right? So it means 1 standard, I'm going to say standard deviation, standard error, but it's supposed to be standard error, is 1 standard error within the our mean of these proportions, right? So an experiment does not provide strong evidence against a claim of a 40% treatment effect. So we can't say either way whether or not our treatment was worse or better, right? Because we failed to reject our null hypothesis, which means we don't have evidence. Okay, and then the other part is just a sample. The sample, so the guy that we did over here, our p hat 1 minus p hat 2, give us 35%. We say the sample will produce 35.5% increase in joint pain relief. The difference in sample proportions is within 1 standard deviation of the mean. So the result is not surprising if the error effect is truly 40%. What is that saying? Well, it's just saying, if you're taking these samples out, and we say maybe 40% is the true increase in joint pain. Well, we know that our 35.57% increase in joint pain is not too far away from the 40% value, right? It's only about less than 5% difference. Well, this means that if we're taking out samples, we see a 35.57%. It's only within 1 standard deviation, which means it's pretty close to the value, right? So that means it's within, if we use our 68, 95, 99.7 rule or our standard deviation rule, we know that approximately 68% is within 1 standard deviation. So this means that us obtaining a value around 35.5%, or in generally within 1 standard deviation, we have had about a 68% chance of doing that. So it's not surprising, right? We might see that. Okay. All right, so that's that part. Now it asks, what is the actual standard error of the difference in the sample proportions? Okay, so now we're going to find that standard deviation guy. All right, so first things first, we need our N1 and N2. Now remember, N1 was the people given the drugs. That's 700, the first sample. Okay, and then 300 people were given the placebo. So this is my next guy, so 300. Now my standard error. So this is the formula. You'll see it in class, like I'll write it down. But know that it is a pretty big guy, so I'm just going to throw it in here in Excel, and you can follow along, but in class you'll see me draw it out. or write it out. Okay, so first things first, square root all of it. So remember the standard deviation for a p-hat problem, or this proportion, it was, the square root of your p-hat times 1 minus p-hat over n. All of that square rooted, right? This is going to be the same thing. Now, instead of just 1 p-hat, we got 2, right? So do the same thing, but then in the middle, add. Okay, so do just like what you did before. Okay, so I'm going to use a whole set of parentheses for each part I sum. So I'm opening with 3 of these. So I click on my p-hat. Okay, this is my numerator, right? Times my 1 minus my p-hat, 1, right? Because p-hat 1. Okay, close that off. Divide by n1, because all the 1's go with each other. See, like now the red closed. That means that one of my fractions under the square root is done. So now do the same thing. Okay, oops. No, accidentally hit enter. Okay, so now open 2 parentheses again. Just like before, we opened with, for this one part, we had opened with red and ended with red. The square root's the black, so we don't want to end that until the very end. Okay, so now we just do the same thing, except now instead of using p-hat 1, we do p-hat 2. Okay, so you click on p-hat 2 times 1 minus p-hat 2. Okay, so there we go. That's my numerator. Divide by my n2. Okay, close off that part and then close off the square root. So see, this is like the standard deviation of p1, and this is the standard deviation of p2. Sum the two of them together. If you think about it like that, that's your standard error for these guys. Think of it kind of like 2 different standard deviations being summed together. It looks horrible, but you guys will have practice. Okay, so that is my standard error. So that would be this guy right here. So my about 3.2%, and I got about 3.2%. All right. So now, how does the actual standard error affect your conclusions from the previous part, if at all? Okay, so now it's just asking again, how many standard deviations does it fall within our conclusion, right? So it's asking you to find basically your upper and your lower. So almost kind of like, these are almost kind of like introducing you into your margin of error problems. Okay, well, if we add our standard error to our p-hat 1 and p-hat 2, so how many times do I have to add my standard error to my difference in p-hat to get up to 40%? So you can just check that out. So let's do, let's see, my p-hat 1 plus my standard error. Okay, so 38, so not quite to the 40% yet, right? So not 40%. So this means it's not within 1 standard deviation. Okay, I'm just checking to see if it's past a certain number of standard deviations, which is if it's beyond 2 standard deviations, or in this case falls outside of 3 standard deviations, standard errors of the mean. Sorry, we can reject the null hypothesis. Remember, that's that whole idea. It's just that we don't actually have to find our alpha. We're talking in terms of standard deviations or standard errors, not our alpha. So let's see how many standard deviations. If it's about 3 standard deviations, then of course we're going to reject the null hypothesis, because if we have if we're 3 standard deviations away, then this means that our p-value is going to be very small, right? So that's just what they're doing here. This is just the easiest way to do it. Okay, so let's click on this guy again. So now we're adding another standard deviation or standard error. Now we're at the 40%, right? So this means that it does contain 40%. So it contains 40%, and that's within 2 standard deviations. So my solution is going to be this. The increase in joint pain relief still falls within 2 standard errors of the mean. Therefore, there is no change in the conclusion, right? Because if it still falls within 2 standard errors or 2 standard deviations, it means I'm still in the acceptance region. That's just what this means. So that's kind of the easier way to just check. I would just say, hey, if my assumed value is greater than my calculated difference for my sample, add standard deviations, or in this case standard errors, until you get a value larger than it and count. Okay, it's within 2 standard deviations. Or if it wasn't there, like for oh, it still doesn't contain my 40%, then I just keep going until it does, right? And then this would be within 3 standard deviations. So just that's kind of the easiest way to do it, right? That's how I do it. And then that's how we would answer that problem. So most of these are pretty much the same thing. They're like, what is the increase in proportion affected subjects from P2 to P1? This just means what is your percent difference from your second proportion to your first proportion. So that just means P at 1 minus P at 2. Well, they give you P hat, or P1 is 0.78, and they give you P2 is 0.52. So we just put them in here, so 0.78 and then 0.52, and your P hat 1 minus P hat 2 would be about 26%. So that's pretty much all of these guys. And then down here, it's just some simple multiplication. So it's asking you for what's N1 times P1. Well, your P1 is 0.51 and your N1 is 500. So we're just checking to see if these two different proportions, if both of them are approximately normal. And remember, in order to have an approximate normality in proportions, you have to have N1 times your P1, or your N times P and your N times 1 minus P. Both of those have to be at least 10, right? So all you have to do is compute these values. Pretty simple. Okay. And then the sampling distribution of 2 sample proportions is shown. Estimate this and this. Right? So if it's a normal distribution, you just throw it right in the middle. And this guy also is a normal distribution, just throw him right in the middle too. So so it's right around that area, like 85%. Yeah, like right here in the middle, somewhere between 0.45 and 0.51. So yeah, I'd say 0.51, right? This black, this tall bar here. So yeah, kind of hard to see. There's no way to zoom it in, is there? Dang it. Well, here this is this tall bar here looks like it's just right after 0.85, right? So then it would be, I would say, it's 0.86. So let's see what happens if I put 0.5, maybe 2, and then I put 0.86. So see, I'm putting one here on purpose because I know it's 0.51. But what if you look at it and you're like, oh, I think it's a little closer to this guy than this guy, right? So let's just see if it is pretty exact. Okay, so it still lets you. It still is a little free with you, I guess. See, their solution was 0.51. So I guess you just get it close, like in the general vicinity. I don't think it's too strict, but that's just how you do those guys. All right, so let's go look at the last problem. These are just like our margin of error problems. So if you were okay with those, perfect. If you weren't, then here's a little more practice. Okay, so let's do this. All right, so suppose a researcher conducts an experiment with 500 people, in which 500 people are randomly chosen from U.S. population. 250 people are randomly assigned to the treatment and control groups. Okay, so our sample sizes are equal. So my N1 is 250, and my N2 is 250, right? That's just what this says. 250 people are assigned to both of my groups out of the 500 people. So now it says suppose 170 people in the treatment group had the desired effect. Okay, so this just means my P hat 1 will be how many people had the desired effect? 170. So it would be 170 divided by my 250, right? Because my that's my N1 and my N2. Right now my P hat 2 is 30 out of those 250 people that had the desired effect. So maybe the placebo or this control group, they knew what was going on. Okay, so there we go. So 30 people with control effect. Use a 95% confidence interval to estimate the treatment effect. UZ equals 1.96. Okay, so my confidence level 0.95, right? You can find your alpha and then manually compute your z, but a lot of times they give it to you, so we'll just use it. 1.96. And now I need my margin of error. Now first off, look here, because I left everything in here, I keep my standard error, right? I don't have to type the stuff in again. So make sure when you guys are doing this stuff in Excel, try to save some of your code, especially if like if you're doing a test and you are you finished a really tough problem, like you finished typing all the stuff out like I just did for your first problem, and what if they had 3 or 4 problems just like this? Well, then if you use your code, so see here, I'm not really your code, but you call up the cells in Excel and you keep calling them up, then all you have to do is change these values. Like what if instead this isn't 0.68 and this is 0.55? See, right away, changed. So make sure you guys are doing this, because it'll save a lot of time, not only on your homework, but on your test. Okay? So there's my p at 1 minus p at 2, so on. There's my n1, n2, and then here, here's the entire formula, right? So remember, that's the entire thing that you're going to do. We did it in our other problem, in the other homework, so I'm not going to do it again, just because it takes a while. So there we go. This is my standard error, or like your standard deviation for 2 samples, pretty much. That's how you can think about it. But they call it standard error. Okay? Confidence level is 95%. My Z star, remember that special Z score, is this. How do you guys remember how to find your margin of error? You take your special Z star times your standard deviation, or in this case, it's the standard error. Okay? And there we go. So it's about 7%. So now we need to find a lower bound and an upper bound, right? So this part's the simple part. My lower, now remember, we're talking about interval to estimate the treatment effect. So this is, we're comparing the treatment of the treatment group and the control group. So we're trying to figure out, okay, how much better was the treatment than the control group? That's why we have my p hat for my control group minus the p hat for the, I'm sorry, not control group, the p hat for the actual treatment group minus the p hat for the control group, right? So we're seeing that this is my treatment, so this is treatment, and this right here is control. So we're seeing that what is the increase of proportion from here to here? So in other words, what's my p at 1 minus p at 2? Well, 56%. So that's a pretty strong increase, right? Okay, so my lower, remember, now we're talking about the differences, or the amount of increase. So instead of your lower being either p at 1 or p at 2, it's going to be the difference between the two. So this guy. Okay, so my lower, then you subtract off your margin of error, right? It's just your p hat 1 minus p hat 2, that guy, do him first, then minus your m. Okay, so then what do you guys think this one's going to be? Well, pretty much the exact same thing. The only difference now is we're finding an upper bound, so you got to add your margin of error m. Okay, so click on your difference between the two, sum your standard error, or sorry, your margin of error, and there you go. So we found our two values. So now they want it to 5 decimal places. Remember to look at this, not this example. Sometimes when they give you that example, they'll say round it to 5 places and only show you a value to 3 places. Try not to look at this. The reason they show you this is because in case you forget what a decimal looks like. This is an example of a decimal. It's kind of funny, but you know, whatever. Remember that these are the directions. It tells you to round to 5 places, such as is giving you an example, and sometimes it's a bad example. Okay? So we're rounding it to 5 places, so let's just make Excel do it for us, right? Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's copy these dudes over. Throw them in here. Copy this one over. Throw them in here. Check the answer. Hopefully you don't get the red death. Ah, we got the green happiness. Good. All right. So this guy's the same. Try him. This one was the margin of error for the confidence interval. This is calculate your margin of error. So it's like doing this whole process, but not calculating your upper and lower, right? Just calculate the margin of error. So you should be able to do that. Margin of error, so do this again. They're trying to get you practice for finding your standard error now, and then a margin of error after that. Suppose treatment group, 95% confidence interval. You said at which confidence interval section the treatment was an effect, or there was a treatment effect. Hey, should be able to do this one, right? Let's see, which confidence interval suggests there was a treatment effect. All right. So what does this mean? Okay, so this means that, remember, our treatment effect is you take your p hat 1, which is your treatment effect, subtract off your control effect. So you want positive differences, right? What happens if you have a positive difference? This means that your p hat 1 is a certain percentage above your p hat 2, right? So this means that, if this guy, so if positive, then treatment effective. Effective. If negative, treatment not work, right? It's for pretty, speaking of caveman terms. Alright, so treatment not work. If 0 is contained, so like we have 0 or really close to 0, treatment might, let me just do that. Treatment might not work at all. Right? No change. Okay, so that's kind of our 3 cases. So sometimes 0 will be contained, right? So like here, so here it's negative, so this wasn't very effective, but then there's a chance it could have been a little effective, but 0 is also contained. So we can't really assume that it was a positive effect. So just look for the values, I think that what they want you to do is just look for the values that actually have an effect. So here, this is a positive, treatment is effective. Treatment does not work, then 0 contained treatment might not work at all, right? Actually, there's probably a better way to think about this, because they're going to say, which suggests there was a treatment effect. Okay, so actually, treatment effect, if positive, treatment effect, let me add one little thing here, is positive. Treatment doesn't not work, it's just treatment effect negative. And if 0, treatment does not work at all, so there's no change. That's how I should have put it, I think. So think about it like this. If it's positive, then this means that, hey, it worked, and you get a positive outcome, right? The drug is good for you. The good is good. It stopped whatever it was supposed to stop. But if it's negative, this means the control group actually did better, right? The control group was better, which means the drug might be bad, right? So this means the treatment effect is negative, right? This means, oh no, the people who didn't take the drug were actually feeling better than the people who did. But then, of course, if 0 is contained, this implies that the treatment doesn't work at all, right? That would imply that p at 1 minus p at 2 is 0. So this means that there's a 0% change between the two. Okay, so you kind of don't really want that. Okay, so which confidence interval suggests there was a treatment effect? So that's kind of where I got here. That what a treatment effect just means, hey, was it a positive effect or a negative effect? So it means just any non-zero effect, right? Well, this guy here says this guy doesn't include 0. This guy doesn't include 0, right? It's about 4%, 12%, 1% to 14%, negative 14% to negative 4%. So 0 still isn't there. But look at this. Negative 0.07 and 0.01. This means this guy does include 0, so we cannot. He could imply that there is no treatment effect at all. Okay, check that, and there you go. So that's how we do that problem. Most of these are, yeah. I mean, you should be able to do this now. So this is just one of those crazy guys, right? You're just doing your conditions you have to be met. So you have to say it has to be at least, what is this? This has to be at least 10, right? This has to be at least 10. This has to be at least 10. And this has to be at least 10, right? Because that's kind of the central limit theorem ish thing, but for proportions, right? They all have to be at least 10. Same as before, right? When we did our when we were doing our sampling distributions, you remember your n times p hat and then n times 1 minus p hat. Those had to be at least 10. This is the same thing. The only difference now is we have two different samples. So we have to think about, well, we have n2 and we have n1. So how does that change? Well, these guys are the exact same. And then down here, you just compute the values. So they give you them here, right? So all the problems. So the 22 random people from all 50 states in the U.S., 46% of the treatment group obtained the desired effect, well, 40%. So 46% would be your p hat 1, 40% would be your p hat 2. So just go through and do these, where your N1, each of which consists of 22 random people. So your N1 and your N2 were 22? Wait a minute. I think that might be trying to trick you. Yeah, 506. Because what happens is it's 22 people from all 50 states. So 22 random people from all 50 states. That would be 22 times 50. So 22 times 50, right? Would that be it? Yeah, it seems kind of strange. So what is the standard error? You should be able to calculate that. This means your N1 and your N2 are both the same thing. So that should work. And then my N times P1, well, that would be, well, yeah. I'm pretty sure that's how you would do it. Because if I do my N1 times P1, what was my P1? My P1 was 46%, so it would just be this guy times 0.46. So 0.46? Yeah, so then this guy would be 506. So 506. Let's see if that was the first answer. Yeah, it is. 506. So that's how you do that problem. You guys should be able to do that. Fill out the rest of these. Just follow that formula, and you're okay. Does that make sense? I know the wording is kind of weird, but it says each of which consists of 22 random people from all 50 states. This means that each state has 22 people. So if you want the total N1 and total N2, you have to do 50, your 50 states times 22 people, or 22 per 50 per state for 50 states, right? Okay, so you have to multiply those two guys together. Okay, and then you should be able to do this. You should be able to do this guy, and so on. You should be able to do the rest of these. That is pretty much it. If you guys have any questions, feel free to talk to me during class or after class, or during my office hours, or feel free to email me. Okay? You guys have a wonderful day, and have a nice week.